Hi again, and welcome to the last part of Lecture 4 of the course Galaxies at Stockholm University, fall term 2025. In this one, we are going to take a closer look at stellar populations. We have looked a little bit into that before, but we have basically only dipped our toes. This time, we are going to dive in a little bit deeper than before. If we revisit what we talked about earlier with the Hertzsprung-Russell diagram and the color magnitude diagram, we remember that a stellar population, if it all has the same age, we can basically determine that age by the point along the main sequence at which the stars have turned off the main sequence and into the giant branch, because these stars here are lower mass and expected to live longer than the ones up here, and so on. So that means that if we imagine that we now have multiple stellar populations, we can start seeing a number of overlapped populations like these with different ages, which means that the image will become much more messy and harder to interpret, but not impossible to interpret. But first, we need to have a couple of definitions in place. The first one, which is the most important one, is the star formation rate, or the SFR. And the SFR is simply the rate at which stars are formed in the galaxy. So it is how many solar masses of star are formed per year in a galaxy. Oftentimes, we also use, which I haven't shown on this slide, but we also use what we call the specific star formation rate, which takes into account that some galaxies are more massive than others, because there's a very big difference between how impressive that is to form 10 solar masses of stars per year, depending on whether the galaxy is the size of 1 million solar masses or 10 billion solar masses. So the specific star formation rate is simply the star formation rate of a galaxy divided by the stellar mass of that galaxy, which tells us something a bit more about how intense the star formation is in that galaxy. The star formation history is simply just a timeline over how the star formation rate has evolved over time. So that is basically just like a curve of the star formation rate as a function of time. And this star formation history, once we integrate under that, will of course show us the exact amount, the exact number of stars, the exact stellar mass that has formed. But from the curve, we will also be able to see when, at what time it has formed. So we can reconstruct the star formation history by fitting observed properties to stellar population models, or by studying the color magnitude diagram of galaxies or globular clusters with single stellar populations. What we see here is various examples of stellar populations, either single age or multiple ages. Actually, I guess this could simply be... Now, these are all for the same metallicity, so basically different ages, right? And you see different age intervals here and where they individually fall on the Hertzsprung-Russell diagram. You can also see that in the low mass end, it is a big old mess, but in the higher mass end, you can actually see different populations kind of separating out from each other. And what the takeaway point from this plot is that you can, now you can see it, is that basically once we have this good models of stellar populations, multiple age stellar populations, we can of course also go the other way and observe relatively complicated stellar populations and still fit them to a number of different populations of different ages and metallicities. And this means that we can actually, if we can measure individual stars in such a population, we can come up with a very good idea of its star formation history. For example, disk-dominated galaxies will have a generally running quiescent star formation. It means that the star formation rate is relatively low, but constant over a large time span. On the other hand, ellipticals and bulges will basically have zero star formation going on today, but they will have had a very steeply declining star formation histories in the past. And finally, in irregular galaxies, you are more likely to see episodic star formation histories, or in other words, you are more likely to see star formation histories that takes a break, then a spike in star formation activity, then a break, then another spike, and so on. And these are what we see examples of here to the right. First, here we have an early type galaxies, which way back in time had rather steep star formation, but then it basically cut off and ended. And after a long time of zero star formation, we see that there's basically no main sequence left apart from the very low mass end. And almost all the stars have broken off to the red giant branch or completely died. The second example here is a spiral galaxy, where you see that there is a very strong bursty star formation in the past. And now over a long time, we have had modest but more or less stable star formation for a while. And here you see that you have the same kind of remainder of an old star formation as you had in the elliptical galaxy. But on top of that, you also have some sort of main sequence out in the high mass end. It is not very strong, it is not very prominent, but it's definitely there compared to what it was in the elliptical galaxy. And finally, we see a small irregular dwarf galaxy here, which has a very strong episodic bursty star formation history. And here we can see that there are also the remainders of an older star population, like there are in the other ones. But on top of that, we also see that there is a very strong and very prominent main sequence, even out to very, very large masses, very young stars, because we basically have had quite strong star formation going on until this very day. And all this is more or less possible to reconstruct simply from these Hertzsprung-Russell diagrams and a set of very, very complex but manageable models of star formation histories and stellar populations. And of course, some assumptions about the initial mass function and so on. And that leads us as a perfect segue onto talking about the initial mass function. So the initial mass function, as I have described in earlier lectures, is the mass distribution of stars when they just formed. It is actually equivalent to the mass distribution of clouds that a giant molecular cloud will break up into, and these small clouds will then each individually form a star. So assuming all stars form instantaneously and at the same time from the same gas, then the initial mass function is the mass distribution of those stars at age 0. And this IMF depends both on the metallicity and the temperature of a gas. What we see here on the right is like a pedagogical illustration of what a typical initial mass function looks like. These are not accurate numbers, but they are accurate enough that they give you a good intuition for how they look. And you can say that for every one star we have, which is between 10 and 100 solar masses, We have 200 stars which are less than half a solar mass, about 50 stars which are between half a solar mass and 2 solar masses, and about 10 stars which are between 2 and 10 solar masses. So you can see that there is a very strong declining slope, and that very massive stars, just like very massive galaxies, are very rare compared to the low mass ones. You can also see that the slope actually becomes a bit less steep when we are in the low mass regime over here. This is not the case for all initial mass functions, but it is the case for this one. You can also see that there is a cutoff value here at 150 solar masses. This is also not a set and done value. We know that for stars about the metallicity of the sun, the cutoff value is somewhere in the vicinity of 100 solar masses. It means that stars more heavy than this don't form. But we also know that for lower metallicities, stars exist all the way out to 300 solar masses, or perhaps even more than that. So the functional form of some of the most important attempts that have been made to formulate the initial mass function, the most important, or let's see, the original grade one of these, the OG, was the Salpeter IMF from 1955. This one is not 100% accurate. It is an oversimplification, but it is actually still surprisingly accurate. And it is still also so simple that it is very nice to learn from. So we are going to be spending quite a lot of time in the company of the Salpeter IMF. And what you see is that by definition, the number of stars in a given mass bin, or in a given mass interval, is this function here, the value of the mass function at that mass times the width of the mass interval. So this here is what we call the initial mass function. Actually, this is just the mass function, but it is the initial mass function if we take this at age 0. And the initial mass function in the Salpeter formulation is simply the mass in each mass bin to the power of minus 2.35 plus or times a normalization number here, which we call phi 0. So this is the Salpeter initial mass function, simply m to the minus 2.35. A more modern initial mass function is the Krupa initial mass function from 2002. This function is more accurate, but it is also more complicated, so we don't want to spend a lot of time with this one for the purpose of this course, simply because we don't gain a lot of extra insight from insisting on using this, but we will have to do an awful lot of extra work, and we just don't want to do that. But what do these IMFs look like? Here is a very nice plot of various IMFs. The straight line here you see in log space is simply just the Salpeter IMF. It just has a single value of the slope, as you saw before. The Krupa that you saw before as well, as you can see, has more than one value of the slope. It is this one. And the slope changes in various mass regimes. And you can see that there are other ones that are even more wiggly around this, but they form the same general shape, that smaller, more lightweight, less massive stars are way, way more frequent than the really high mass ones. We will be playing more with these in the exercises later along in this course. We are actually going to be spending quite a lot of time in the company of IMFs, so you can all be looking forward to that. And that's about it for today. Thank you for staying with me this long. All we have left now is the discussion questions that I want you to mull over until we meet on Wednesday. The discussion questions are question A. Why do AGN show variability in their luminosity? I actually kind of already answered that in the lecture, but you should think about whether you can think of more or more detailed explanations for this. Explain why AGN in particular can give rise to very fast and very large amplitude variations. And question B, the IMF can be determined by observing nearby stellar clusters. Discuss how this could be done. Can you think of another observational method to constrain the bright end of the IMF? And that was it for now. Again, thank you for staying with me this long. I hope I will see you again soon. And until then, have a nice one.